Good evening, everybody. Tonight's video, we're going to cover a couple of topics. We're going to start with even and odd functions, and then we're going to talk about average rate of change. And both of these topics are something that we've actually already talked about. We just haven't called them these specific terms. So we'll make the connections to what we've talked about, and then we're going to also look at these in a new way. So even and odd functions. We've already seen what even and odd functions look like. They were symmetric to the y-axis and symmetric to the origin. So even functions, if we're looking at the graph, are symmetric to the y-axis. So that means they look the same on both sides of the y-axis. So if we have a little coordinate plane here, if I have something that is an even function, it's going to look symmetric to the y. So that means whatever happens on one side of the y-axis, it's going to look the same over on the other side. With odd functions, since they're symmetric to the origin, remember, it's more of like a diagonal sort of symmetry. With the y-axis, it's easy to see, you just fold it over and see what's on one side and the other. They should be the same. With the origin, remember, there's like a diagonal. We can always drop points diagonally through the origin. And if there's a point equidistant on the other side, then that means it's symmetric to the origin. So we've seen this. We've talked about that already. But now we're going to try to translate that into function notation. So remember that this is kind of how we would define whether or not a graph was symmetric to the y-axis. We would say if xy is a point on that graph, then negative xy is also a point. So if here is xy, then over here would be negative xy, right? Because it would be the opposite of the x coordinate. Same thing with an odd function. If we had xy as a point on the graph, so let's say here's xy, negative x, negative y, so switch both coordinates, would also be a point on the graph. Okay, so that's how we've defined it before. Now thinking of that in terms of function notation is what we're going to talk about now. So for even functions, if I say that x is xy is a point on the graph, then the opposite of xy is also a point on the graph. So that means the y value that's associated with negative x is going to be the same as the y value that's associated with x. So we can say f of negative x equals f of x. Same thing with odd functions. The y value that's associated with negative x is going to be the opposite of the y value that was associated with x. So see how this is the y value that's associated with x, and now its sign has changed as well as the x sign. So over here, the sign of the x changes from positive to negative, but y stays the same. So that's why those two are equal. The sign of x is changed, but the function evaluation stays the same. Down here, the sign of x has changed and also has the sign of y. So that's why when x switches from positive to negative, the whole value of the function is also switched from positive to negative. Okay, so let's explain that a little bit more with an example. So we want to determine whether each function is even, odd, or neither. Like we mentioned, if we had just the graph, it would be easy. We would just check to see if there was symmetry to the y-axis or the origin. But if we don't have the graph, we just have the equations, we're going to do some algebra. And like we just said, if it's an even function, f of negative x equals f of x. And if it's an odd function, f of negative x equals the opposite of f of x. So what we'll do here is just evaluate for f of negative x, because that's the first half of both of these statements. So f of negative x, right? I just want to see if that either equals f of x to tell us that it's even, or if that equals the opposite of f of x to tell us whether or not it's odd. So that's what we're going to do. We have a function here, f of x. So the first thing I do is evaluate f of negative x. So if I have f of x equals x squared minus 5, I want to evaluate f of negative x. So this is just like plugging in. If I asked you to do f of 3, you would just replace the x with a 3. So here we're going to replace the x with a negative x. Negative x squared minus 5. I always like to put that in parentheses because now I'm going to simplify. And what this is saying is it's negative x times negative x, right? Because it's squared. So negative times negative is positive. So that would be positive x squared minus 5. Okay, so now I have two things to check for. One, I want to see if it equals f of x. And f of x equals x squared minus 5. And when I look at f of negative x, that also equals x squared minus 5. Okay, so this would be an even function, right? So this is even because f of x equals f of negative x, right? It's the same thing here. So this is an even function. Now it's easy because I just see f of x here. I can just check and make sure they're the same. Checking to see whether or not something is odd is a little bit more involved. You actually have to also determine what is negative f of x. So what is the opposite of this whole function? So we'll figure this out first, and then we already know it doesn't match up, but let's just double check. So the opposite of this whole function, so I'm going to take the opposite of, and then I put all of f of x into parentheses, and now I'll distribute that negative. So that's going to be negative x squared plus 5. And so I can see that f of negative x does not equal negative f of x. So that's how I can tell that this is definitely not an odd function, but it is even. Okay. Let's try another one. So we'll say g of x equals x cubed minus 1. So the first thing we want to do is check and evaluate g of negative x. So we plug this in, negative x cubed minus 1. And now let's simplify that. Negative x cubed, negative times negative times negative remains negative, right? So it's cubed, it's times itself 3 times. So this is negative x cubed minus 1. All right, now I see that that is not the same as g of x. So g of x is x cubed minus 3. This is negative x cubed. I'm sorry, that's x cubed minus 1. This is negative x cubed minus 1. So it's not even, right? These two are not the same. G of x and g of negative x are not the same. So let's check and see if it's odd. So now I'll take the opposite of g of x and evaluate that. So now I have the opposite of x cubed minus 1. And so when I simplify that, I'll get negative x cubed, but this negative times negative 1 becomes plus 1. So this does not equal g of x, and it does not equal the opposite of g of x. So this one is actually neither. So it's neither even or odd. Okay, so neither even or odd. Okay, so basically what you're going to see here is we're doing 3 things. First thing that I always look at is the function. I'll write it down in blue because if it matches up, blue is the color I've been using for even functions. Then I evaluate the function for negative x. We figure that out and see if it matches up with my blue one, then it's definitely even. The third thing I do is I take negative whatever the function is, so the opposite of the function value, simplify that, write that out in purple, and then if I see that that matches up with g of negative x in this case, then I would know that it was odd. Okay, so I just do 3 things. I write out the even, I write out the odd, and then I evaluate g of negative x and see if it matches up with either one. In this case it doesn't, so I know that it's neither. There's one more. I'd like you to do this one on your own. So h of x equals 5x cubed minus x. Try doing this one on your own and bring that to class tomorrow to determine whether or not that is even or odd. Okay. Now there's one more thing we want to talk about tonight, and that is called average rate of change. And again, very similar to what we were just saying with even and odd functions, there's one way to say this that we already know, and then there's another way to say this using function notation. So remember, we have already talked about slope. We've talked about slope of a line, and we refer to it as the change in y values over the change in x. Remember, that's a delta. That's a Greek letter that looks like a triangle and always means change of. Okay, so slope is the change of y over the change of x. So we were doing y2 minus y1 and x2 minus x1 when we were dealing with slopes of lines. But now we're talking about stuff in function notation. So average rate of change is still our change in y values over our change in x values. But remember that y values, when we're talking about functions, we replace the y with f of x, right? So this is going to be a change in our function values over our change in our x values, right? So I'm not going to be talking about y's and x's anymore. So when we think of average rate of change, and we're going to think of this in terms of function notation, we're going to say that average rate of change will be written as f of b minus f of a over b minus a. In this case, we're going to say b cannot equal a, right? Because if it did, we'd have a 0 in the denominator. This would be undefined. But we're going to describe average rate of change using function notation, where f of b minus f of a over b minus a is what we're going to call average rate of change. And that's where b does not equal a and a comma b are in the domain of f of x, right? So if I have some function and I pick two elements from the domain to find the average rate of change, I will plug them into this expression, f of b minus f of a over b minus a. So let's do a quick example to show you what I mean by that. So if we say we have f of x equals 3x squared, and we want to find the average rate of change from 1 to 3. So in this case, I'll call this a, and I'll call this b, and here we have f of x. So I'm going to set this up as f of b minus f of a over b minus a. So b is 3, a is 1. So f of 3 minus f of 1 over 3 minus 1. So I just plugged in b and a to my expression for average rate of change. Now I got to evaluate that. F of b, f of x is 3x squared. So I have 3 times 3 squared minus f of 1, so f of a, which is 3 times 1 squared, all over 3 minus 1, I can simplify that as 2. If you had a little more complicated function here for f of x, you could put these in like bigger parentheses so that you're evaluating that all separately, like if it was a longer expression, like if you had a trinomial or something like that. Make sure you're doing all of that work to evaluate f of b first, then subtract f of a. Get it as simplified as possible before you do the subtraction. That'll make it easiest for you. So we have 3 times 3 squared, so 3 times 9, which is 27, minus 3 times 1 squared, which is 3 times 1, which is 3. So we have 27 minus 3 all over 2. 27 minus 3 is 24 over 2, which is 12. So the average rate of change here is 12 over 1, or 24 over 2. So if this was representing the slope of a line, it would be very steep. It would be a slope of 12. But in this case, we're just talking about average rate of change, and we're going to talk more in class. I'll tell you what this actually means. It's called the slope of a secant line. But we'll talk a little bit more about that later, connected to what you'll do in the future in calculus. But for now, you'll just be able to calculate the average rate of change from two values in the domain of f of x using this formula here, f of b minus f of a over b minus a. Okay, so bring that other example where you determined if h of x was even, odd, or neither, and bring your notes for average rate of change with you to class tomorrow, and we'll work on some practice problems, and I'll see you then. Have a great night.